My name's Amy Sullivan, and I'm the current Vice President of AAAR. It's my pleasure to welcome you to the 28th in our monthly series of AS&T lectures. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, the editors of AS&T select a high-impact paper to be presented by its authors. With these lectures, we hope to be able to highlight the amazing research happening in our community, tie our journal to other activities in AAAR, and also give us an opportunity to come together outside of the annual conference. In addition, each of these lectures is being hosted by one of our student chapters. And so I want to thank all of you for joining us and everyone who's helped to make these possible. And with that, I'll turn it over to our student chapter from the University of Miami to get us started. Thanks.
Thank you, Dr. Sullivan. On behalf of University of Miami's AAA student chapter, it's my great pleasure to welcome you all to today's AS&T lecture. We are honored to have with us a distinguished speaker whose contributions to the field of aerosol chemistry are both significant and inspiring. Dr. Sergey Neskorodov is a faculty member in the Department of Chemistry at UC Irvine. He has earned his PhD in physical chemistry from Basel University, Switzerland, and expanded his expertise through postdoctoral research in chemical kinetics and reaction dynamics at University of Colorado Boulder, and also in atmospheric chemistry at California Institute of Technology. Dr. Neskorodov has a rich history of research and teaching that has greatly influenced the field of aerosol science. Over the year, Dr. Neskorodov has received numerous awards for his research, service, and outreach, including Fulbright scholarships, AAAS Fellowship, AGU Ascent Award, and the Koblenz Award, to name a few. He has also served as the AAA President for the year 2020-2021 and is widely recognized for his inspiring work in aerosol chemistry. Today, Dr. Neskorodov will be presenting on light-absorbing products of atmospheric oxidation of indole by hydroxyl radical, nitrate radical, and ozone. We're fortunate to have the opportunity to hear from such an expert and a thought leader. Without further ado, please join me in welcoming Dr. Sergey Neskorodov. Dr. Neskorodov, the floor is yours.
Well, thank you very much for this wonderful and kind introduction. I'm always feel embarrassed when people say distinguished and this and that. So it's really, I'm just fortunate to have a wonderful group and they produce really nice results. So this is the paper that AAA Aerosol Science and Technology has chosen to highlight in this presentation. So so I thought about this, and it's kind of difficult to talk about just one paper. And given that we published 3 papers on indole SOA, I decided to talk about all 3. I will, of course, highlight the one in the middle, in Aerosol Science and Technology, but I will also tell you about the starting paper from 2017 and the paper we just submitted in 2024. So I would like to acknowledge support by National Science Foundation and NOAA, and from AUCI, and acknowledge our collaborators in Purdue University and Weizmann Institute of Science. And I underline the names of the people who did the most for this paper. So me, I mostly sit in the office and come up with molecules to study, such as this indole molecule. So this talk will be mostly about brown carbon. So I would like to remind you what brown carbon is. So the attention was, so people were interested in brown air pollution for a while, and there were lots of papers in early 2000s attracting our attention to this. These are some photographs from a paper by Ramanathan from 2007 showing brown clouds over different parts of the globe. And brown carbon is recognized as important for climate and visibility. And one way to look at its effect on visibility is to look at its effect on absorption, aerosol absorption optical depths, and compare what brown carbon and black carbon are doing. By the way, I'm using BRC, which is not bromine carbon. This is brown carbon as an abbreviation sometimes, so that you're not confused. So this analysis was done in 2012 by Bahadur. And he looked at the absorption aerosol optical depths and here at 675 nanometers, depending on where you look. Of course, the largest absorption comes from black carbon, but brown carbon shown in green, also makes a sizable contribution. And what's more important, as you go towards from the red to blue, the relative importance of organic carbon relative to elemental carbon grows. So it's really quite important, especially in the near UV and blue colors of the spectrum. So we can define brown carbon by contrasting its properties to black carbon. So the black carbon absorbs light at all wavelengths. It's essentially soot. And then organic carbon doesn't generally, most organic molecules actually don't absorb too strongly, but some of them do. And sometimes you encounter an organic material in the atmosphere that's visibly brown. And brown carbon can be defined as organic carbon with non-negligible absorption coefficient in the visible spectrum. Non-negligible, I mean relative to soot. So I would like to comment on a misuse of brown carbon definition. I often get to review brown carbon papers, and people often state that brown carbon only includes molecules that absorb visible radiation, and they do not include molecules that don't absorb visible radiation. At first sight, there is nothing wrong with this statement, but I view it as inaccurate and often ask people to change it for the following reasons. All molecules absorb radiation, just the extent differs. And another thing, oftentimes the absorption spectra of brown carbon is determined by so-called chromophores that are very strong absorbers that are present in minority concentrations, and it's very difficult to separate them from less absorbing organics. But more importantly, it's not just molecules that do the absorption, it's supramolecular complexes as well. The spectrum becomes dependent on humidity and concentrations and presence of other things. So a better way of doing this, and this is what Saleh did in 2020 in his review paper, Rawat Saleh, is to classify brown carbon by the absorption coefficient. Okay, he classified it into very weak, weak, medium, and strong. And this is the classification that I think is very good, and we are going to stick with it. So then for those of you who don't take absorption spectra too often, what makes the objects appear brown? Brown is not a pure color. There is a joke in physical chemistry community, bring me a brown laser, but the brown laser doesn't exist because you cannot have a pure brown color. So in order to generate brown, you need to absorb some blue and some green. And in TV screens, in RGB TV screens, you make brown by combining some red and some green in different proportions. For example, if you take an RGB scheme, if you take 150 units of red and 75 units of green and no units of blue, you get this beautiful brown color. And in print, you do something similar. We of course don't do RGB. It's too crude, so we take absorption spectra with very high resolution. And in fact, it is the wavelength dependence of the absorption spectrum of absorbing species in aerosol that drew attention to brown carbon in the first place. So this is a very important paper for brown carbon history that recorded absorption spectra of molecules. And typically, absorption spectra, empirically, they appear to follow a power law. The mass absorption coefficient, MAC, is wavelengths times the power of minus absorption angstrom exponent. And for black carbon, angstrom exponent is about 1. So there are theoretical reasons for this, and that's what people observe in the field. For organic species, it's steeper than that, so the dependence is steeper than that. And based on the analysis of different samples, Lack and Kappa recommended that absorption angstrom exponent in excess of 1.6 indicates the presence of brown carbon in the sample, absorbing organics. All right. So where does brown carbon comes from? The major source is combustion. So there is hulis, tar balls, and both contain PAHs that are substituted, and this is really a major source. So you can also have some amount from fossil fuel combustion. So there was a review already a while ago in 2006 on this topic. And there are also secondary sources. There is secondary brown carbon, and I underline photooxidation of PAHs, not because it is the most important source, it's actually probably not, but because that's what we are talking about today. And already in 1999, Jacobson proposed that nitrate PAHs are important contributors to light-absorbing carbon. You can also produce it by OH oxidation of aromatics in water, by chemistry of carbonyls, aldol condensation, imine formation. If you form SOA in acidic seed, sometimes it absorbs colors. There was a review in 2015 in which I participated, and it's probably time for another review. Another big one on brown carbon because it's a popular topic. All right, so let's go closer to the topic. So what about NO3? NO3 is an oxidant that's very important at night. It builds up and oxidizes biogenic and anthropogenic hydrocarbons. And it was noticed that reactions of NO3 with aromatics can actually produce light-absorbing species already a while ago. For example, in this 2019 paper by Inon Rudig, they looked at tar balls and they exposed them to conditions where OH and or NO3 were present, and they noticed that the refractive indices, both complex and real, behaved in a complicated way as a function of aging. And then in a paper by Rawat Saleh's group, they also looked at the evolution of light-absorbing properties, and they were exposing, they similarly produced primary aerosol that was rich in aromatics by burning, and they were oxidizing it further by NO3, and they found that absorption coefficient goes up with the degree of aging. So brown carbon from you can also produce secondary brown carbon. So the previous examples was aging of primary brown carbon by NO3, but you can produce secondary brown carbon by reactions of NO3 and heterocyclic aromatics in the gas phase. So there were two papers by, I would like to highlight a few papers, there is more, but there were two papers by Ireni's group that showed that if you take heterocyclics, like this one with oxygen, nitrogen, sulfur, and oxidize them by NO3, you produce fairly strongly absorbing compounds. And Rafael Mayorga, I've seen him on Zoom in the audience, published a very nice paper dealing with mechanism of oxidation of pyrrole-related species shown here, and that also produces brown carbon. And 2024, there was a publication on indole SOA, so it was independent from us. Another group also took indole and oxidized it by OH in presence of NO2, and sometimes the conditions would favor NO3. And I'll mention this paper again. But the bottom line, there is quite a bit of interest in this NO3 plus heterocyclic aromatics chemistry. So indole, why indole? Indole is actually fairly common in the environment. We see it both in our homes and also in nature. So this is some of the common molecules. So this is how indole looks like. So you've heard of tryptophan. Some of you may actually take it as a supplement. Indigo is used to color your genes. Indole 3-acetic acid, very important in metabolism. So indole exists in nature. And it is used in perfumes, pharmaceuticals, and dyes, and agriculture. So by itself, its smell is not very pleasant in high concentrations, but it actually smells pleasantly in very low concentrations. That's why they add it to perfumes. It is what attracted our attention I remember listening to a conference, I think it was Gordon Research Conference on Atmospheric Chemistry, and people mentioned indole emitted in response to stress. And that's what led to the goals of this study. So we looked at what was done on indole previously. Rate constants for indole reactions were measured by Atkinson group. So it reacts very quickly with OH, so it's almost gas kinetic. NO3, so this really attracted our attention. Very fast reaction with NO3 and very slow reaction with ozone. So it's very interesting. So Atkinson also figured out what was the major gas phase product for reactions of OH, and this was formaldehyde. So what we wanted to do, we wanted to look at the composition and properties of indole SOA using different oxidants, OH, ozone, NO3. And we wanted to look at key properties, real and imaginary refractive index, and we wanted to know what the chromophores are, and we wanted to model it if we can. All right, so I'll start chronologically. So this is paper number 1 out of 3, and was written by Dr. Julia Montoya Aguilera. She received her PhD from us in June 2020, and poor Julia could not participate in the hooding ceremony that year because, if you recall, it was COVID. So we hooded her virtually, as shown here. So what Julia is doing now, so she's an air pollution specialist for the South Coast Air Quality Management District, and so very happy about this job. So what she did, she took a chamber, so injected indole in it, oxidant. For this first study, it was hydrogen peroxide, turned UV lamps on, and collected the sample and studied it. So she learned very quickly that it produces aerosol in very high yield. So this is a very high concentration example, but it sort of illustrates the points. You add indole, you start oxidizing it, indole goes away, secondary organic aerosol builds up, you calculate the yields. This is both in micrograms per cubic meter, and the yield here is actually more than 1. Because you oxidize it, it becomes heavier, and it all condenses in the particle phase. So there are gas phase products there, of course, but a lot of the products sit in the particle phase. It is brown, all right. So it produced beautiful brown carbon samples. This is an example of a Teflon filter. This is how it looks when it is extracted in water. If you take absorption spectrum, it looks like this. Mass absorption coefficient is of the order of 1 meter squared per gram. For reference, soot would be about 10. So it's sort of medium strength brown carbon. So you take the logarithm of mass absorption coefficient versus logarithm of wavelengths, fit it, that gives you the angstrom exponent. It's of the order of -6, which is pretty common for brown carbon. This is how we calculate mass absorption coefficients. We take absorbances through these solutions and then calculate them. So we wanted to know what's there. So we used 2 methods. One, okay, sorry about the acronyms. High performance liquid chromatography, photodiode array absorption spectroscopy, high resolution mass spectrometry. And the other is nano desorption electrospray ionization, high resolution mass spectrometry. So for HPLC, what you do, you take your sample, you dissolve it, you run it through the column. As things come out from the column, you take the absorption spectra with photodiode array, hence the PDA part, and you compare it to standards. And then you take high resolution mass spectra, and that gives you elemental composition. So this is very good for if your focus is on light absorbing compounds. So PDA is a critical part here. If you just want to know what's there in the sample, so this is great. This is what we started with actually. So nanodecies, it was pioneered by Alex Laskin for atmospheric aerosols. The great thing about it, you don't need to pre-extract the sample. You just shove the filter under, you dissolve it on the fly, and it goes into the mass spectrometer. So we'll start with nanodeci. This is how mass spectrum looks like. This is molecular weight here, relative abundance. So there is monomers, basically dimers and trimers. And indole itself has 8 carbon atoms, and the most common products still have 8 carbon atoms, but there are also dimers, C15, so there is some dimers that will be a little destroyed. So you can build a histogram of how many carbon atoms molecules contain. So here is 8 as in indole, here is 16 as in dimer. In this particular case, the average molecular formula is around C15. Well, it's good, but it doesn't tell us anything about what's absorbing in this sample. For this, we turn to liquid chromatography. So you scan them in the retention times. As they come out, you record the absorption spectrum as a function of wavelengths. Each reach here corresponds to an absorber. And then from high resolution mass spectrometry, you get the formula. Okay. So the chromophores are mostly dimers. So for example, we found dihydroindigo, tryptophan, then dihydroindoxyl red, indigo dye, indirubin, indoxyl red. All of these are actually quite well-known products of indole oxidation. Okay, we confirmed what these things are by the absorption spectrum. This is so here shown in blue is the reference from the literature, and in black our chromatogram. It's not a perfect match because you have to understand in the literature you have a pure compound, and we have coeluting species. At every retention time there is something else coeluting. You never get a pure absorption spectrum, but this is a pretty good match. You know, this peak and this peak. This is a pretty good match. This is a good match. We have high degree of confidence that what we are looking at is the correct molecules. You can come up with a quote-unquote mechanism. It's not really a mechanism. It's a sequence of oxidation steps. You start with indole in the gas phase. This is your gas phase product. We actually see it in PTMS. And then you go to 3-ox-C indole, so you see that as well. You oxidize it. This CH bond is pretty weak, so you oxidize it. If you dimerize it, you get dihydroindoxy indigo dye. Oxidize it further, you get indigo dye. So this, you can produce an Ara2 radical from this and produce izatin. And then this is indoxyl red. And this it's colored because it's highly conjugated, and indigo dye is also highly conjugated. So from izatin, you can make anthralinic acid by oxidation, and then anthralinic acid combined with izatin again gives this molecule that I cannot pronounce, tryptanthrin. So we see it also as one of the major products. All right. So in this paper, we were very bold and decided to actually model this. So we introduced this reaction going from indole to half indigo dye in the Caltech Irvine model of South Coast air quality basin. So that model has this basin digitized as a function of height and as a function of position. There is 200 gas phase species, 600 reactions, and that many particles, different sizes, different species, and we added this one reaction to it, and we considered different cases. The base case, 0 emissions of indole, then low emissions. Actually, I wouldn't call it low, but we called it low in the paper. 5% of biogenics is indole. That's actually sounds pretty high to me. So medium emissions, 10% of biogenics, and high emissions, like impossible, that's probably really upper limit, 25% of biogenics. Yeah, that would be a very strange scenario. And then we also did high emissions, and we haven't studied NO3 chemistry in this paper, but we've added it into the model based on the recommendations from reviewer. So what we find is that indole could contribute to visibility, but the contribution is low. So this is the additional aerosol. You know, this is Riverside, Anaheim, Long Beach, Los Angeles. This is additional aerosol produced by this chemistry. And this is high emission scenario, and we're only talking about 0.1 microgram per cubic meter, so it's not a whole lot. But the interesting prediction was that indole plus NO3 is actually more important than indole plus OH, based entirely on these modeling predictions. And I'm sorry, this is a complicated graph. This is concentrations integrated over the entire domain as a function of hour, from midnight to midnight. And this trace in black, this is the baseline concentration of SOA in microgram per cubic meter. Just actually high at night, lower at daytime. And then here, this is additional concentration due to the indole chemistry in percent. So in the low emissions scenario, SOA goes up by about 1%. In the medium scenario, SOA goes up by about 3%. And in the high, it goes up by about 10%. But what's interesting, if we include NO3, it is also happening at night because NO3 is so reactive. It's just as reactive as OH. So the next step, then, we decided to investigate NO3. So the paper number 2, that's the one we are highlighting today, is chemistry of indole plus NO3, ozone, and OH under high NOx conditions. We just decided to cover all of the oxidants. It was done. The experiments were started by Julia Montoya Aguilera, and then continued by Baboomian. So this is a photograph of us right after Hooding. He got his PhD in 2022 and now works as an environmental scientist in York Engineering. So right away, I want to tell you the result. Indole NO3 is the winner, #1 in terms of absorption. So it generating this black and sometimes dark green, sometimes purple colored filters. It was really marvelous to watch. Indole plus OH, that's the one we studied previously, so sort of less absorbing, and indole plus ozone is not too absorbing at all. All right, so we've done the same things. So we recorded the chromatogram. So here is indole plus OH from previous paper. This is the new one, indole plus NO3, and then indole plus ozone. And then what really stands out, this is normalized, so it's hard to tell, but this really stands out. So the nitro-indole peak really stands out in the indole plus NO3 SOA. Also, if you look, these peaks appearing in the visible are also stronger in the indole plus NO3 SOA. So we decided to pay a bit more attention to this one. So here are mass absorption coefficients for indole plus OH, indole plus OH plus NOx, indole plus NO3, indole plus ozone at different relative humidities. Red is dry conditions, black is 25% relative humidity, and blue is 50% relative humidity. And if you look for indole plus OH, okay, you increase relative humidity, the aerosol becomes a bit more absorbing. For ozone, you increase relative humidity, aerosol becomes a bit more absorbing. But what was remarkable is that for NO3, the dependence was non-monotonic and it was reproduced. I'll show you later. So this is the nitro-indole peak, and it's high under dry conditions, and it really drops by a factor of 2 at 25% relative humidity, but then it gets up again in magnitude. There is something going on that's non-monotonic with respect of relative humidity. For indole, OH, NOx, we didn't do the relative humidity dependence, unfortunately. So we wanted to measure the refractive index, and we asked Inon Rudig to help us with this because he is really a master of these measurements. So what they can measure is the real refractive index. So that's very important to predict the scattering by aerosol, and imaginary refractive index. And that's a fundamental property of the material from which aerosol particles are made, and they're related to light absorption. We measure mass absorption coefficient of the bulk material in our experiment, and we can calculate K from this. And just to get you oriented, if you're not familiar, if you take a material with mass absorption coefficient of 10 meters squared per gram, which is soot, roughly speaking, you get a refractive index of the order of 0.4. So that's a very strong absorber. This is for 500 nanometers. I've done these calculations. If you go down one order of magnitude, so at 1 meter squared per gram, so you get K of the order of 0.04. That's a medium absorber. Another order of magnitude, 0.1 meter squared per gram. It's 0.004 weak absorber. And generally, per Saleh, if you have K below 0.001, it's a very weak absorber and generally not going to be too important for climate or visibility applications. Okay, so all right, I apologize for small labels, but we plotted the logarithm of refractive index as a function of logarithm of wavelengths for all of the types of aerosols that we made. So this is nitration under different humidity, OH oxidation under different humidity, ozonolysis under different humidity, and just dry OH plus NO2. So that for brown carbon, it's supposed to look a straight line here. So it's a bit wavy because of the nitro-indole and this dimers present there. But you get an effective angstrom exponent of the order of 4 to 6. And if you put it on this Saleh 2020 classification, which is plotting log of K at 550 nanometers, which is a peak of the solar spectrum, as a function of angstrom exponent, so you get this domain, which is a very weak brown carbon, medium brown carbon, and strong brown carbon, and soot will be there. somewhere. And then, so the points fall here, so it's characteristic of, even though filters look very, very dark, it's still a weak brown carbon, actually. So what Ian Rudi's group has done, they produced aerosol from indole using the oxidation flow reactor. Actually, they had 3 reactors, one for ozone, one for NO3, and another one for high OH in presence of NOx. And they've done measurements with the method that they use based on broadband cavity enhanced spectroscopy that can measure absorption spectra of size selected particles, and then through modeling you can get both real and imaginary refractive indices. They have to use 2 cells, one more to the UV and one more to the visible, because simply because the mirrors you cannot get mirrors that are reflective over the entire range of interest. This is not the actual setup that they used. This is from a earlier paper that developed that. But they used a very similar thing. So with 2 cells and making it by oxidation flow reactor. So here are the measurements from Weizmann Institute of Technology. So let me go through this. So this is wavelengths. This is, let's start with the real refractive index. And there is 2 sets because they have 2 broadband cells. And they do it, this is for indole plus NO3, and they do it at relative humidity that's dry, so it's high, but then it goes down, all the way down at 25% relative humidity and back up at 50 and up again at 70. If you look at the imaginary part, it's of the order of 0.1, so it's pretty strong actually. So again, you start at a high value on the dry conditions, which drops at 25% relative humidity and then creeps back up at higher humidities. Offline at UCI for indole plus NO3 produced by a different method. This is in chamber, this is oxidation flow reactor, but qualitatively we see the same thing. Under dry conditions, we have a high K, and which drops to 25% relative humidity and increases back up. So you have this complex effect of relative humidity and absorption coefficient with a minimum of 25% RH. And this is reproduced by 2 independent measurements. So one offline absorption from filter samples and the other cavity enhanced absorption from particles. So what it tells us is that there is probably 2 competing mechanisms for making light absorbers. One probably operates under dry conditions and another operates under humid conditions. So we can't really tell. So we didn't get enough information to answer this question. You may say, okay, does it show up in the mass spectra? It does, and I apologize for complicated graph, but this is high resolution mass spectra. So this is indole plus NO3, dry conditions on the left, 25% relative humidity in the middle, 50% relative humidity on the right. This is normalized relative abundance of different ions. The top one here is nitrate indole. So it comes out at this retention time. And this is a logarithmic scale. So it is higher under dry conditions, drops under 25% relative humidity, and increases again at 50% relative humidity. Very similar to what absorption spectra are doing. And you see there is also non-monotonic dependence for some other ions. So we asked Ian and Rudi's group to do AMS measurements on their secondary organic aerosol, and they also see non-monotonic dependence on humidity in the AMS families. So these are different families. So the black is carbon, brown is carbon hydrogen, and there is NH family and all the others. What's important here, this is relative humidity. And again, there is this non-monotonic dependence. Under dry conditions, you have a value for, let's follow this brown family, which I believe is CH. Under dry conditions, you have lower signals that increases and then decreases again. And then blue, let's follow this blue signal, and NO signal increases and then decreases again. Again, so there is this mass spectrometry evidence that something is going on with absorption coefficient. So now you're all expecting me to answer why there is a minimum in the mass absorption coefficient and 25% relative humidity. And we wrote a whole paragraph about this in the paper, but the best way to summarize this paragraph is this quote from Mark Twain. It ain't what you don't know that gets you in trouble. It is what you know for sure that just ain't so. So what I'm trying to say, there are many ways water can affect absorption coefficients by directly participating in reactions, by affecting viscosity and supramolecular interactions between molecules. We really don't know how exactly it affects absorption spectrum in this particular case. So, and this is good. So we can do additional experiments, additional calculations to figure it out if we want to. So this study was very satisfying, but it left a few questions unanswered. And so I'm going to share you with the results produced by Dr. Avery Dalton. This photograph is how many days? 3 or 4 days old. So he was hooded just a few days ago, and just before he was hooded, he submitted this paper, isomeric identification of nitroindole chromophore in indole plus NO3 organic aerosols. And he will soon be a scientific programmer with Applied Research Associates. So very nice. So what was the motivation for this follow-up study? By this time in 2023, we had a paper that I just discussed by Baboomian that found nitroindole in the indole plus NO3 as secondary organic aerosol. So this band here is due to nitroindole. Jiang and others also published a paper that essentially found the same band under the conditions when NO3 chemistry is possible or NO2 is present, you get this very strong nitroindole band that dominates the spectrum. We basically just wanted to know which isomer of nitroindole you're producing. So we're getting really chemical here. See, the indole has 1, 2, 3, 4, 5, 6, 7 different hydrogens. So theoretically, 7 isomers of nitroindole are possible. So we just wanted to know which one. So the goals here are to identify the dominant nitroindole isomer. And this sort of gives the answer. It's going to be this one on the 3rd position. So this is the numbering. We are using nitrogen as 1, and then 2, 3, 4, 5, 6, 7. And then determine the mechanism by which this nitroindole is formed. And for this, Avery has done calculations with density functional series. So I'm going to show you the results. So the analytical part of this was really satisfying. We were able to confirm the isomer using optical, chromatographic, and formula confirmation. It turns out that you can buy most of the isomers. We couldn't buy the C2 isomer, but C3, C4, C5, C6, and C7 are all available. We bought all of them. We recorded the absorption spectra, and we were in luck. They were all very different. Okay, so this is really as different as it gets. You can very easily distinguish this isomer by absorption spectroscopy. All right, so we ran the chromatogram of the indole plus NO3 secondary organic aerosol. A PIX comes out in the photodiode array channel. And then we ran the standard 3, 4, 5, 6, 7. And then for each one, we recorded the absorption spectrum. And so I'm going to cover the ones that don't match so that they don't obscure the discussion, but it's a clear match. Retention time matches to 3 nitroindole and absorption spectrum matches to 3 nitroindole. What's even more remarkable, it's just one isomer that we are producing. This is a retention time. This is photodiode array spectrum. And then the second panel is total ion current spectrum. Red is positive ion mode, black is negative ion mode, and then this is selected ion current spectrum corresponding to just nitroindole. If there are multiple isomers of nitroindole, you would see multiple peaks in this spectrum, but there is one major peak in both positive and negative ion mode. There is maybe tiny blips here. You might be able to produce other isomers, but clearly one isomer dominates and contributes heavily to the absorption of the whole SOA. Furthermore, with Lisa Winen, we recorded aerosol mass spectrometry spectra of 3 nitroindole standards that we aerosolized, and indole plus NO3 secondary organic aerosol that we produce in the chamber, and they look very similar. So there is a characteristic peak at 162, which is actually ionized nitrate indole, and there is a very close match. The fact that this spectra are so close, this is a unit resolution spectrum, and this is a high resolution breaking it into family. The fact that there is such a close match between this and this suggests that nitrate indole is a majority species in the aerosol, and this is consistent with what Jiang 2024 paper found. And this is some of the ions you can actually use to, especially 162 and 132, if you want to go and look for nitrate indole in the field, these are potentially useful ions to find it. So what is the mechanism? So in this paper that I already mentioned from 2024, they said, okay, so what's going to happen? OH or NO3 is going to attack indole, abstract the CH atom, and then NO2 is going to add. So, and this is what the mass fraction they reported in SOA, very high. So really it's dominated by one product. This is all fine. The only problem with this proposal is that if you look at the bond dissociation energy for CH bond at the carbon 2, carbon 3, carbon 4, 5, 6, and 7, carbon 3 is actually has the highest bond dissociation energy. There is really no reason to abstract hydrogen atom from the 3 position. If anything, that's the last position you want to abstract it from. But what's interesting, so this paper here actually calculated bond dissociation energies for all of them, including nitrogen, and the bond dissociation energy for NH is low. Okay, this in combination with the previous study on pyrrole oxidation prompted us to reconsider the mechanism. So we are going to abstract hydrogen atom not from CH bond, but rather from NH bond. It's more probable. So this is the reaction scheme. So you start with indole, NO3 comes in. It doesn't have to be NO3, can be OH, and takes this hydrogen atom away. It's the lowest bound hydrogen, so it goes away. So you form this free radical, but what's interesting, this free radical is not super happy. So it actually converts through resonance to this radical. And now you have the radical site at the correct position. And now NO2 can come in and add. You still have this is still not nitrate indole. You actually have to get rid. You have to have this hydrogen atom migrate to this nitrogen. And we actually don't know exactly how it happens. So we suspect by tunneling. And you end up with 3 nitrate indole. So basically, compared to this mechanism, only the initial step is different. So you don't abstract hydrogen atom here, you abstract it there, and then you isomerize. So we've done Avery, Avery has done calculations of the energetics. So you start with indole, the delta E plus 0 point energy is red, and blue is delta G. So delta G is more important for the prediction. So you start with indole at 0. You abstracted a hydrogen atom to produce nitric acid, and because nitric acid is stable, this is actually down in energy. There is a barrier for this. So to get from here to here, so you have to overcome a barrier, but you end up actually down in energy. And then if you attempt to optimize this radical, it actually converts into this one, and the spin density is mostly on this carbon atom, and you're down in energy some more. And then you can continue. NO2 comes in. So again, we re-zeroed the energy. NO2 comes in, and 32 kilocalories per mole down, you have your 50 kilocalories per mole down, you have your nitrate indole. So it's there is a small barrier on this of the order of a few kilocalories per mole, but it's fairly easy to overcome at room temperature. So it all makes sense. So this was a very satisfying result, and so this is where we are. with indole chemistry at the moment. And I was told to speak for 45 minutes, and I think I'm making good time. So I'm going to summarize the lecture. So if you take indole and you oxidize it, you produce secondary brown carbon. And oxidation by NO3 is especially good at that. So if you oxidize it by NO3, you collect this beautiful dark filters from the chamber. So based on our modeling, it can make a contribution to SOA, but it's pretty small. So if people are interested in looking for contributions of nitrate indole and indole oxidation products, the best place to look is probably downwind of animal husbandry facilities where indole is produced in high amounts. But of course, these facilities produce a lot of organic molecules in high amounts. So nitrate indole is a major product of indole plus NO3. What's remarkable is just a single isomer, 3-nitrate-indole, is produced, and it's definitely confirmed by comparison with standards. So reaction starts by abstracting the hydrogen atom from the NH bond. We showed that it's not by NO3 addition. I didn't talk about this, but NO3 addition doesn't work, or CH abstraction. And there is an unanswered question about the non-monotonic effect of humidity on the absorption coefficient, and we don't really have an explanation at present. And so with this, will be happy to answer any questions you might have.
Thanks for the great presentation, Dr. Niskardo. So let's see if the floor is open for questions. So if you could please type into the chat. I think we have one viewer who is. So if you could unmute yourself and ask the question to Dr. Niskardo directly, or you can type it in chat and I can read it out to him. We can't hear you clearly, Peng Jian. Okay, in the meanwhile, I have one question, Dr. Niskardo. So you said that the nitroindole it has a multimodal peak in that absorption curve, and it behaves differently for different humidities. So how do we model that how do we model that in terms of mass absorption coefficients? I'm not an expert in atmospheric chemistry or aerosol chemistry, but just a question.
Well, it depends on what you want to model. I mean, I'm not a modeler, but you really can't put too much in a model before it becomes too complicated. So in the one attempt for us to model this chemistry, we disregarded the humidity dependence completely. We just added one reaction going from indole to a product, and we assigned some sort of volatility to this product and some sort of absorption coefficient to this product. So if it's formed, that's what you get. And that already produced that's already a model that's sort of hard to run, so time consuming. So I don't think people generally put relative humidity dependence of absorption coefficients in any sort of air quality or climate models at the moment. It's just too much information. But it's just fundamentally interesting that water can participate in reaction one way or the other. So it's more of a chemical interest, I would say, than of interest to modelers. If it was the case that humidity completely shuts down brown carbon production, that probably would be such a dramatic effect that could be modeled, but the effects are more subtle, you know. It's still absorbing, just less.
Right. So we have one question in chat. So Nishit Shetty asks, even with the oxidation chemistry you showed, the brown carbon generated was weak or very weak brown carbon. What are your thoughts in terms of what are the constituents of the mild brown carbon and strong brown carbon that you showed from the Rawat Saleh? And is it an SOA from larger polymers responsible for this or something else entirely? So two-part question.
Yeah, so I think, I think this higher order polycyclics, if you have more rings in your system, so it's a more conjugated system, and you produce polycyclic aromatic hydrocarbons and substituted polycyclic aromatic hydrocarbons in combustion, and the bigger they are, the more absorb. Eventually, when they become really big, you eventually get something that's soot-like in absorption. So it's probably 3, 4, 5, 6 ring polycyclic aromatic hydrocarbons that may be oxygenated and nitrated that produce the strongest light absorption signals. So from the point of view of a photon, you get a large absorption coefficient when you encounter an extended conjugated system, and this is what large pHs give you. So these are probably the molecules responsible for strong brown carbon species.
There's another question in chat by Feng Jiang, and he says, "Hi, Sunny. Thank you for citing my paper. Could we see 3-nitro-indole in field measurement? And could we simulate indole products in the globe?"
Maybe we could see it in the field measurements. I mean, the people who do high resolution mass spectrometry and publish list of formulas that they've seen have seen this formula. It is there. It probably corresponds to 3-nitro-indole. We wanted to actually take a look at some field aerosol mass spectrometry data, and we asked Qi Zhang whether it's a good idea to analyze AMS. Based on her input, people generally don't trust assignments of peaks at such high, we are talking about M/Z 162, and the resolving power of AMS is just not high enough to assign peaks with certainty. And generally, the high resolution mass spectrometry analysis does not extend past about maybe M/Z 130 or so. So if you expect this molecule and you're looking for this specifically, so you might be able to find it in the aerosol mass spectrometry data. So you might also, now that you know the absorption spectrum, you might be able to find it in liquid chromatography mass spectrometry data. So we haven't made a concerted effort, but we feel these papers provide enough information for people to look for this molecule if they are so inclined. So my perception of atmospheric environment, if you wanted to find a molecule there, you will find it. Just the question is, what is the concentration?
And I think the follow-up question was, could we simulate indole products in the globe?
Could we simulate indole products in the globe? I suppose one could, but again, to what purpose it's not clear. So it appears there is just not enough indole to make a dent in the direct effect of aerosols on climate. It might be important in some highly special locations where, for one reason or another, there is a lot of indole, but around the globe, globally, it's not going to make an impact. There is just not enough of it in the planet.
And Katie Kolozwari says, "Great talk and thank you. You mentioned that there was a minimum at 25% RH in terms of nitro-indole production. I was wondering if you had done any experiments between completely dry conditions and 25% RH.
No, we just went in steps of 25%. And basically, it takes 1 day to run a chamber, and you need to run replicates. There is just not, and because you also use different oxidants. So if you try to use too many relative humidity points, it quickly becomes out of control in terms of the amount of time you need for your experiments. So we have not tried this.
Still, I don't see any other questions in the chat for now. We can give a minute to see if any questions. Anyone still wants to ask any question?
Well, if not, it's okay too.
Yes. Yes, that sounds good too. But then that brings this month's Aerosol Science and Technology lecture with Dr. Sergey Niskorov to a conclusion. Thanks everyone for joining and listening to this lecture. And we'll see you all at AAAR hopefully in October. So have a nice day, everyone.
Okay,
Thank you,
thank
Dr.
you, everyone.
Niskorov.
Bye.
Thank you.